All right, thank you so much for the opportunity to present today. I think the timing with the previous presentation is very interesting. So I'm a master's student in Rafael Nejmatovic's lab, and I'm going to be presenting our development process on how we were able to get a Python-based open source virtual screening software. So our starting problem is that around 80% of proteins have no known potent binders. There's this target central resource database that categorizes proteins into 4 different categories. And just to simplify them for our presentation today, 2 of them can be combined and become sort of a chemically neglected class where you have no known potent binders and very little knowledge about the protein function. And then you have another category that I've called extensively studied, where you have all this data. So out of the over 20,000 proteins, there's only about 13% that have really strong known binders. And the other side effect to being neglected is that we don't really have good structures, and quite a few docking software struggle with this issue. So one of the results I was able to get was thanks to this publication last year, which published all the results for docking with Glide on APO, AlphaFold 2, and hollow structures. And what we can see is that while Glide performs very well with hollow structures, its performance gets almost cut in half when using APO or AlphaFold 2 structures, especially when they're not refined. Another issue is speed. One of the fastest docking softwares that's available right now is Dock, which is around 1 second per molecule, and this is without counting any sort of pre-processing steps. So if you wanted to screen all of zinc 22, which is over 10 billion compounds, with 1,000 CPU cores, you'd be looking at over 100 days, which is not really feasible. We managed to get that down to around 0.1 second per molecule. The other thing is that a lot of these software need quite a few complicated pre-processing steps, which often require extra software for which you have to get licenses. So our goal was to simplify all this and make docking as accessible as possible. So this is kind of a summary of my presentation, but we started off with the scoring function from FlexAid, which is software that was previously developed by our lab, and increased the speed by simplifying it, which gave us NRGDock. And then we did three tests. The first one was a benchmark with APO and AlphaFold 2 structures using .e, which I'll explain more further along in the presentation. The next 2 steps were a virtual screening experiment with 50 million molecules from enamine, as well as all the 102 targets from .e to look at non-property match decoys. And finally, we looked at predicted ligand specificity. So the scoring function we started off with sort of has 3 parts. The first one is protein-ligand interactions. The next one is protein-solvent interactions. And the last one evaluates any clashes. What we found is that we could remove these last 2, only keeping protein-ligand interactions, and even simplifying this down more to only keeping into account pairwise energy between a ligand atom and a protein atom. So to kind of illustrate this graphically, in our pre-processing steps, for which we only need 1 software that we developed, we define a binding site. We then index protein atoms into these cubes that are around 6.5 angstroms in size. And then for each one of these cubes, we say, if a ligand atom was in this cube, what would its binding energy be? And that binding energy is just the sum of its pairwise energy between the ligand atom and any protein atoms that are within 1 cube. So we're going kind of deep into the protein when we're considering interactions, but this allows us to have some sort of implicit flexibility. And then when the software runs, all it has to do is do an exhaustive search of ligand poses by moving the ligand onto one of these dots in the binding site, and then just adding up the pre-calculated binding energies for every single one of the atoms. So if you have a ring, for example, that's all within the same cube, each of those carbon atoms will have the same contribution to the binding energy, which traditionally with other scoring softwares has not been the case. So the first method we used to quantify our performance was using this directory of useful decoys, which has 102 proteins from various different families, as well as 23,000 ligands with a known binding affinity. This results in around 224 ligands per protein. And each of these has 50 decoys that are very, very similar, but just changed slightly enough so that in theory they wouldn't bind. And what this allows us to calculate is an enrichment factor, and in this case, an enrichment factor at 1%, where we start off with a certain amount of true binders for decoys, and what we want is in our top 1% to have more true binders than decoys, a better proportion than what we started off with. So an enrichment factor of 4 means you're 4 times more likely to find a true binder when you pick from our results than if you were to randomly pick molecules. So when we look at our results for AlphaFold and APO structures, we can see that due to the high variance amongst each families, in this case, APO is blue and pink, NRGDock is blue and Glide is pink, or for AlphaFold 2, NRGDock is green and Glide is yellow. We can see that our enrichment factors are fairly similar. Glide might have slightly better average, but statistically, it's very, very hard to say for sure that they're different. One thing that's interesting to note is that the true binders that we find, so the binders for which NRGDock gives a very good score, usually Glide ends up giving them a bad score. So our software is finding different true binders than what Glide is finding. And the same is true for AlphaFold 2 structures. We also looked at hollow structures, and in this case, NRGDock does perform slightly lower, but once again, there's a big variance amongst the targets. But when we compare our results to Glide, which we're very lucky to have all this data published, we see that we find molecules that Glide doesn't. So our method that we're presenting is so easy to use that we kind of would like to use it in combination with other methods and look at the best results for those. So next, we did this ultramassive virtual screening. We took 102 targets and scored 48 million molecules from N-amine, as well as known binders, which in this case we define as EC50, Ki, Kd of less than 1 micromolar to make sure that they're very good binders. And what we plot is the scores, docking scores of true binders versus this random set of molecules from N-amine. And what we can see is that NRGDock gives much better scores. So in this case, lower is better because it's an energy. NRGDock gives a much better score to true binders than the random molecules from N-amine. And of course, we have this long tail from the molecules from N-amine, which means that we potentially have new binders around here. But our software is able to differentiate between these true binders and random molecules. So the final step that we looked at was PIM1, PIM2, and PIM3, which are 3 kinases from the same family. And we did the same thing as before with known binders as well as molecules from N-amine. What we can see is a clear shift between the two, which reveals that our software is still differentiating between known binders and these random molecules. The other important thing to note is that our structure for PIM3 comes from AlphaFold. And even with this AlphaFold structure, we still have this difference. One issue that could be brought up by using these cubes that are so big is that we might lose ligand specificity. If 2 ligands are fairly similar, they might have the same score, so NRGDock would get confused between the ligands. But what we found is that among the best binders for PIM1, we have some candidates that score very low on PIM1, but get a much worse score on the other kinases. So hopefully these molecules are more specific to this one kinase than others. The final step would be to validate all of these experiments in vitro. So we currently have 4 collaborations going on where we're exploring this. And in one of them, we have one potential candidate that we're just a few experiments away from knowing if it truly binds to the receptor. So the results that I kind of want to highlight are that we get similar performance to the industry standard, which is Glide. Although the advantage of our software is that the pre-processing is less than 1 minute compared to, for example, Dock, which is close to a day and needs extra software. And we're around an order of magnitude faster than Glide. We also still have the ability to differentiate between true binders and non-property match decoys. And as well, we can still find specific molecules even by keeping into account this implicit ligand flexibility. So on that, I'd like to thank everyone in our lab for all their participation, especially Olivier Maillot, who's now at UCSF. We're going to publish our tool soon. We're just waiting on the preprint to be done. And of course, all the source code will be published on GitHub for you guys to use. So thank you.
Yes, thank you. Thank you. Do we have any questions for Thomas?
Hi, very nice work. So I was curious, I may have missed this, but how are you handling the ligand conformers?
So with our, sorry, I'll just go back to the beginning here. The way we pre-calculate the score for the ligand is that we say it can be anywhere within this cube, which is around 6.5 angstroms, and it'll have the same score. So this, we tried generating conformers with our DKit. We went up to 1,000 conformers, and the score didn't change. The docking score didn't change. So by taking into account this ligand flexibility with these big cubes, we don't need to generate conformers, which saves a lot of time.
Okay, thank you.
Do you have more questions for Thomas? Oh, I have one. Oh, you have one as well. You go first.
How do you consider receptor flexibility?
So it's sort of the same explanation, because in here I've highlighted all in gray, and in blue and red would be all the receptor atoms. And these can move within the cubes as long as they're within, at maximum 12 angstroms, they'll be taken into account. So slight movements in the protein won't affect the score of the molecule. So this flexibility is kind of taken into account by that. So you could generate ensembles of conformers of your receptor if you're really interested in looking at that. But what we find is that it doesn't affect results that much.
Does the value of 6.5 angstroms have any special physical significance? Thank you.
We found it kind of by chance, but when we calculated the surface area in contact, what we do is we take the van der Waals radius of the atom, of the ligand and the protein, as well as the radius of the solvent. So in this case, we use the solvent as water. So we got 1.4 angstroms times 2, plus the ligand van der Waals radius, which usually goes from 1.5 to 2. So on average, this ended up being close to 6 or 6.5. And I tested different numbers going from 2 to 8, and 6.5 ended up being the best one.
Cool. Do we have any more questions for Thomas? I have one. So a lot of your analysis has been mostly focused on your ability to identify binders from non-binders. Have you checked your ability to recapitulate the original poses? Have you compared with, let's say, the new benchmark, relatively new benchmarking?
Yeah. So
busters and stuff.
Just like the tool that was presented earlier, we're presenting this as sort of a first step in the pipeline. And because we want to be so quick, we removed any kind of geometry. So the poses that we predict are not very realistic. And this is where more precise docking software like FlexAid or Glide would come into account when we have a smaller amount of ligands. So let's say you would want to rescore the top 100,000 ligands, then you could get a pose with a more precise software. But we also added the ability to include clashes, so that's an option.
And one more question, because I saw you broke down your results per family class. Have you compared performance of other tools that are dedicated, let's say, to predict GPCR inhibitors, kinase inhibitors that are not docking tools, or they're ligand-based, for instance?
Yeah, I haven't looked at that yet. I haven't looked at tools per class, but that's an interesting idea.
Cool.